And welcome everyone. As we go ahead and jump into some AP Calc, we're going to first do some review before we actually dive into the full topics. And I think a good starting point here is looking at linear functions. And the reason why I want to do that is because calculus is really at its heart a fundamental piece of mathematics of change. All right, we're looking at when two quantities are related, how does that one change affect another? So the best way to approach this is through functions, and that's of course very familiar to us. If we are looking at functions from any kind of other view, we know that y equals f of x. F of x, of course, simply just means the function of x, and functions describe how one quantity or variable is going to affect the other. A good example of this is simply how distance walk can be described as a function of time. And when we look at this through the lens of calculus, we're going to ask, if we know how much time has elapsed, for example, can we determine, therefore, how far the person has walked? And this doesn't necessarily just limit itself to changes in time. We can do this in changes in distance, pressure, example. And these are all examples of increments. And what is an increment? Well, an increment is simply just the change in a variable, such from x1 to x2, and we're going to call that an increment. And we represent that change with this delta x. So this delta just simply means change of, and so that is simply going to be the change in from x1 to x2, and we're going to represent that with x2 minus x1. So then, of course, when we want to actually look at this with some numerical examples, let's go ahead and say we want to find the increments of the change of x and change of y from the point 1, negative 3 to the point 4, 5. So let's go ahead and first do the change in x, and then we'll look at the change in y. So our change in x, if we look, we have our x coordinate, remember, is always first. So this is our x1 coordinate. This is our x2 coordinate. So I'm going to set this up as x2 minus x1. And so if I do this first one, my first value is 4. So I'm going to do 4 minus, and I have 1. So this means that the change in x is 3. Now, if we look at the change in y, we're going to look here at the y values. So this is my y1 coordinate. This is my y2 coordinate. The y2, of course, is change of y is the y2 minus y1. And so let's go ahead and just substitute in the values we found. So y2, of course, is 5. And y1 is minus 3. So we have a minus minus. Remember, that's going to go ahead and make that a plus. And so we're going to get 8. So our change in x is 3, and our change in y is 8. Now, this is very important to kind of keep in mind as a good starting point here, because linear functions are very special amongst functions in that an increment of one unit in one variable is always going to have kind of the same increment in the other variable, because we're going to notice we're doing x2 minus x1. We're not using like an x3 or anything like that. Therefore, we can also conclude that linear functions have a constant ratio of the elements. And of course, if you have any kind of preceding math here, you can kind of understand ratio means a fraction. And so that's going to lead us into our definition for what a linear function needs to be. Well, a linear function, the variable y, is a linear function of x if the ratio of the increment of y to the increment of x is constant, such that the change in y, and let's go ahead and fill this in here, is going to be over the change in x, it's going to be constant. All right, so within linear functions, the constant ratio, so this change of y over change of x, of the increments is known as the rate of change. And for us who come from a strong algebra background, might remember that this rate of change is also known as the slope of the line. So if we can define slope, we can define this as having 2 points, so x1, y1 and x2, y2 are 2 points on the graph of a linear function, and we can define slope, or m, of this line as the ratio of these increments. So m is rise over. Some of you might remember this is the rise over the run. And so we already know this from our previous definition. This is simply the change in y, or the change in x. And we can fill that in with the values we looked at in our previous example. y2 minus y1 was our change in y, which means that change in x, of course, is the x2 minus x1. Now, linear functions produce straight lines when they're graphed. A line with a positive slope will go uphill as x increases, And obviously, if it's a negative slope, it's going to decrease. A line with a slope value of 0 is horizontal, since the change in y is 0 and all points have the same y coordinate. If the change in x is 0, though, that means the x coordinate never changes and our line is vertical. We can describe vertical lines, therefore, having no slope, or another way to think about it is that the slope is undefined. So let's go ahead and apply this now with another example. So given a line that passes through the point 2, 3 with a slope of m equals -2, we want to find the y-coordinate point on this line if the x-coordinate is 3.6. Well, we can start off first by solving this by addressing the change in x. So our change in x, we know that with this, we have the x-coordinate is 3.6. So that's our first x value. So we have 3.6. And we know that the other point here is 2, 3. So this is our x. So this effectively is x2, this is x1. So I'm just going to go ahead and subtract these 2 points. So this is going to give me the change in x, which when I subtract those should give me a value of 1.6. Now, we also know that the ratio is -2 because our slope is -2. And because we know because this has to be -2, I can argue that the change in y is actually going to be -2 multiplied by our change in x. Because that's simply just taking that ratio and breaking it back apart. And so when we go ahead and multiply this, what do we get? Well, we get a -3.2. So if we were to say, well, what is our y-coordinate? We can now take this -3.2 and plug it back to get what that missing y-coordinate is. So we have to, of course, look at what's our original point. Our original point is 3. And we are adding to this change value. So it is a -3.2. And once we add those, we can find our other y-coordinate as a -0.2. Let's go ahead and continue this a little bit more here. Let's finding some additional values to the linear function. This time, let's apply this with a little bit more real-life example. So we have the pressure P on a diver is a linear function of the depth D. If the pressure at 20 meters is 2.988 atmospheres, and an increase of 5 meters depth corresponds to an increase of 0.497 atmospheres, we want to find the pressure at 23 meters. So again, if we look at this, it's a linear function, which tells me that I can apply right away a change ratio. In this case, we're using the change in pressure over the change in depth. And now, even though these, of course, are not x and y, we can, of course, still use the same approach. And we know that our change in pressure, remember, it's right here. A change in pressure is 0.497. So actually, I'm going to go ahead and highlight that. So let's switch to highlight mode here. So do a highlighter. So there's our change right there. And our change in depth, we said, is every 5 meters. So with that in mind, let's go ahead and apply our ratio. So our change here is going to be 0.497 over 5. And if we go ahead and work the math on that, we can find that's going to be 0.0994, and that's going to be atmospheres per meter. Now recall, we want to find this at 23 meters, so what we're going to do is we know that at 20 meters we have this many atmospheres. So we can say that when D is equal to 20, and we're going to 23. So this is the change that we're going to make here. So our change in D, or our delta D, is going to be 3. And what we can do then is, again, kind of do a little bit of reverse math here. And I can multiply this by this ratio that I just found. So 0.0994. And that, of course, should give me a value of 0.2982. And that, of course, is just the start, because we need to take this then and bring it back to our actual value of 23. So 23, of course, if you remember, we started here with 2.988. So we're going to take our original y value here, so 2.988. And we're going to add to it our new value that we just found here. So we're adding to it 0.2982. And that will tell me my new y coordinate, which in this case is going to be 3.2862 atmospheres. All right. Now, this approach that we've been doing is slope feeds itself really nicely into the point slope equation of a linear function. And why is that? Well, it's very useful with point slope because we can know an ordered pair, x1, y1, that satisfies the linear equation, and we can know the slope between those point and some other point that will satisfy the ratio that creates that rate of change. And if we multiply this equation by the denominator, we can include an equation that's also valid when xy equals the point x1, y1 itself, which is what we've been using right here to kind of help find that missing value. So again, some quick review here. The point slope equation of a line is y minus y1 equals m parentheses. That means to multiply x minus x1 end parentheses, which you can also write as y equals m parentheses x minus x1 plus, what are we adding? y1. So let's go ahead and use the point slope form to go ahead and create our equation. So we want to have an equation that's going to have a slope of 5, and we're passing through the point 2, 3. Well, all we need to do is plug that back into that original equation. So let's go ahead and write that equation again one more time. Y minus y1 is equal to m parentheses x minus x1. And so if we look here, we can just plug in our values. Well, let's plug in y minus, what's our y1? Our y1 is 3. So I'm just going to plug in 3. My m is, of course, my slope value, so that's just 5. And my x stays there, and x1 we're going to pull right here from this function, or this point, excuse me, and let's go ahead and put that in. And so now our equation is y minus 3 equals 5 times x minus 2. Now this, of course, is a great quick warm-up, but let's go ahead and use this to model a linear function. So we want to use the information in example 3, and we want to find a linear equation that describes the pressure as a linear function of depth. Well, if you remember, we had a constant ratio in here that we were able to find here. And remember, P was our variable that describes the pressure, D describes the depth, and when we set this up, we can, of course, think about this as our ratio of change of P over the change in D. And so using that, let's go ahead and use that to try and think about what was our slope that we found. So let's just go ahead and back up for a second. And if we go back to this example, you can see we already found the slope. The slope was found right here. We calculated this at 0.994 atmospheres. So this is our slope right here. So let's go ahead and use that. And we're going to go ahead and put in here 0.0994. Okay, so that is, of course, our m. Here, that's our slope. And all we need to do then is to find point. Well, we had a point that was given to us, and we can go ahead and plug it in. So let's go ahead and rewrite this as P minus P1 equals M parentheses D minus D1. And with that in mind, let's go ahead and write the equation that we want. So we're going to go ahead and say P minus, and what was that original value that we had here for our P1? Well, if you remember, we had a pressure value of 2.988. That was our original value that we had. And so we can then bring in our M, so it's 0.0994. And we're, of course, using D instead of F here, X. And so now we need our D1. Well, what is our D1 point? We had 20. And this, of course, is the equation that we were able to use from example 3. Now, there are, of course, other linear equation forms that you are probably familiar with. We have the slope-intercept form, which is y equals mx plus b, and the standard form equation, which is ax plus by equals 0. Assuming, of course, that, in this case, a and b do not equal 0. All right? So very important thing to keep in mind there, because if it's equals 0, well, now you just have by equals 0. So these are two equation forms that you aren't going to see quite as much for what we're going to be using here in calc, but they are still equations that you might encounter. For example, slope-intercept is very useful when we're modeling real-world problems that have a fixed part, and a proportionally varying part. The standard form equation is very useful when we're looking at things like linear algebra, so for solving equations, matrices, etc. But let's go ahead and jump into two other types of lines that, of course, we should be familiar with, which is that of a parallel and a perpendicular line. Remember, parallel lines form equal angles with the x-axis and have the same slope. So, for example, I'm just going to make a real crude line here real quick. If I have a line running through here, and I have another line running right through here, if I were to go ahead and measure this angle that's coming through here, I should find that these angles are the same in that x-axis. Now, if two non-vertical lines are perpendicular, and perpendicular means, remember, they're meeting at right angles, so I'm just going to go ahead and make a line here and a line here. You could have two perpendicular lines like this, or if we want to have something that's maybe not quite so horizontal and vertical, we could do that as well. So again, I'm going to make my axis here, make a pretty crude one. So I'm going to have a line that moves through here, and let's say I have another line that comes through here. And these are going to, again, meet at 90 degrees. And because they're meeting at 90 degrees, the slopes M1 and M2 are negative reciprocals, meaning that if I were to multiply those slopes, I'm going to get a value of -1. So with all that in mind, let's go ahead and find equations for these lines. So we have a line that passes through 3, 5, and is parallel to the line with the equation y equals 2x minus 8. And we have one that is going to be perpendicular. We have an x-intercept of 6. And notice we have a standard form equation this time. So let's go ahead. I'm going to switch to blue here to do part A, just so we can make sure that these are nice and clear. So part A here, we have y equals 2x minus 8 as our original line. And if we look at that, what is the slope value of that original line? Well, this one's real easy to identify because we can look right here where x is, and we can see our m. So we know that m is 2. And because I know that m is 2, I know that a line that is parallel needs to also have that slope. So let's go ahead and write y equals 2x. But we need to find what is the y-intercept. All right. So in order for us to do that, we'd have to figure out what that is. Now, the way we can solve this is instead of using slope-intercept form, because we only know the point it passes through, instead of using slope-intercept form, let's instead, I'm going to actually just cancel that out, and let's go ahead and use point-slope form. So we can use y minus y1 equals m parentheses x minus x1. You can start seeing how point slope might be really handy. So I'm going to go ahead and plug in. So I know I have this point here, 5, 3. So I can plug that in. And so that's my y point right here. And again, m we know is 2. I'm going to do x minus, and I have x1. So that, of course, in this case is 3. And so here is the equation of a line that would be parallel. Now for part 2, I'm going to switch back to black here. So for B, we again are looking at a line that is perpendicular. So if we look at this one, we have to wonder, okay, what is our slope? Well, the slope of this one is actually really easy because there's nothing here on the y. I can actually look right here at this x to figure out, oh, well, the slope of this line has to be a certain value. Well, if I move this x to the other side, I could very easily identify that m is -2. And if we remember, if it is a perpendicular line, we know that the perpendicular line, so I'm going to call this M2, I know that it has to be a negative reciprocal, which means this has to be 1/2. So let's go ahead then and use that information now to go ahead and, again, use point slope form to help us out. So we are going to use y minus y1 is equal to m parentheses x minus x1. And we can plug in values. So y minus, what's our y1? Well, our y1 in this case, if you remember, this says it's an x-intercept, 6, 0. Which means if I were to use this, I can plug this back in. So my y is 0. My m, we just said, is 1/2. X minus, what's my x1? 6. And so we can actually even simplify this a little bit more. So I get y equals 1/2. X minus 6. Now, when we start talking about linear functions, these are often very used to represent quantities in the real world. All right, this is not unusual that these relationships might be linear. Now, in calculus, we're more interested in extending the slope concept to other functions rather than necessarily looking at linear functions, but it's still good fundamental understanding for us to review. Now, where this might start coming in handy, though, is where we start talking about solving two linear equations simultaneously, because this might be something we need to apply in a greater scope. So let's say we need to find a unique order pair xy that solves two different linear equations simultaneously. Let's go ahead and take a look at a few of those techniques. So here I have a unique pair that I want to find. I have two equations. I have 3x minus 5y equals 39 and 2x plus 3y equals 7. So I'm trying to find the point of intersection. So there are, of course, three common methods that we can use very easily. First is substitution. We want to start off by, number one, solving for a single variable. And the way I can do this is I can pick one of the equations. Let's go ahead and pick this first equation here, 3x minus 5y equals 39. And so 3x minus 5y equals 39. Pick a variable to solve for. Let's go ahead and say we want to solve for what x is. That means I get 3x is equal to negative 5y plus 39 divided by 3. We find out that x is going to be a negative, or excuse me, not negative, it's going to be 5 over 3y plus 39. So now that we have our x value, we can then take this whole chunk here and plug it back into an equation to figure out what it is. Now, we can't plug it back to the first equation. That won't work. We need to plug it into the second one. So we're going to say 2 of 5/3 y plus 39 plus 3y equals 7. And that, of course, should help us find what our value should be. So once we substitute that in, we can now go from here to solve and get what our y value is. So carrying that 2 through, we should get a 10/3 y plus 39 times 2. It's 78 plus 3y equals 7. We can again combine some like terms. So I can bring, for example, the 78 over. I can combine the 10/3 and 3y. I'm just going to go ahead and skip a little bit here because again, this is some basic math review. So let's go ahead and jump right to the end here. We're going to do y equals negative 3. And now if we want to figure out what our x value is, all I have to do is take that and I can plug into either one of these equations. I think I'm going to do the second one because that just looks a little bit simpler here. So I'm going to switch back to black for this. And let's go ahead and just say 2x plus 3 times negative 3 equals 7. 2x equals, plus a negative 9 equals 7. Then we get 2x is equal to a positive 16, x equals 8. And so we would get y equals negative 3 and x equals 8. And if we write that as a xy pair, that would be 8, negative 3. Now that's, of course, just our first method. Our second method is elimination. We can try to solve this by getting things to cancel out. And sometimes this can work out nicer for us than what substitution might do. So with elimination, we can set these up. So we're going to set it up as, again, the original equation. So 3x minus 5y equals 39 over 2x plus 3y equals 7. And we do substitution here. What we're going to do is try to find something that can get these to cancel. So for example, I might look at this 3 and 2 and say, I can turn these both into 6's, which means that this, of course, is going to become a multiplied by, let's say, 2, and this bottom by negative 3. And that would, of course, allow me to eliminate these very easily. So let's go ahead and make the top then our change here. So this is going to transform into 6x minus 10y equals 78. And our bottom is now minus 6x, and that's going to be a minus 9y is equal to 21. Now, of course, I can just do some basic math here. You can notice that we will have the x's cancel out, and I'll get a negative 19y is equal to 57. Oh, I forgot my negative sign here. There we go. And now with those set, I can simply solve for y. And if we do this, we should, of course, get a negative 3. Should be the same point as what we got before. And with this, now from here, we, of course, can say, oh, we have this. Well, we can then do the exact same process as we did in substitution above. We can plug that in for x up here. So we could, of course, go back to the 2x plus 3 times negative 3 equals 7, and we'll get x equals 8 once again. So both of these are very valid approaches. Now, the other approach that we can do is graphing. And this is the last thing we're going to talk about today, and that's we're going to use our graphing calculator to find the point of intersection. So for that, I'm actually going to switch over to my graphing calculator here. And what I want to do is, on my graphing calculator, go into my y equals here, and I want to put in the two functions. So in order for me to do this, though, I need to make sure that when I set them up, I put them into a y equals form. Notice these are in standard form, so yes, you will need to rewrite them. So our first function, I'm going to go ahead and give these to you just for a demonstration purpose. Let's go ahead and do 3/5, and that's going to be our x. And we're going to subtract from that 39/5. That's our first function. Now for our second function, we're going to want to do a negative 2/3, and that's our x again. And we're going to add to that 7/3. And then we can go ahead and graph those. Now, you may not be able to determine right away what this is, but the way we can figure out real quickly is that we can hit the second key here, and we can go ahead and hit the traces. You can see there's a calc option, so I can do that. I can press 5 for the intersection. It's simply going to ask the two curves I want to check, because if you had more than 2 in here, that would be what you want. But since I only have 2, I'm just going to press enter. I'm going to press enter, and enter one more time for it to calculate the guess. And you can see I get a value of x equals 8 and y equals negative 3. So again, if I had to find that point, I would write that as 8, negative 3. And that's going to wrap up our large review here of everything linear. And hopefully that helps give you a good refresher before we jump into all these different calc topics that we're going to have to talk about.